So now let's explore the relationship of free energy in non-ideal solutions, whereby bonds between A and B are different from AA bonds and BB bonds. For a non-ideal solution, the mole fraction X can be replaced by activity A. What exactly is a non-ideal solution? Remember, we talked about, say, perhaps BA bonds and AB bonds. This way, these are not the same as BB bonds and AA bonds. That means the bond energies are not the same. In a non-ideal solution, we can essentially replace X with activity A. So these equations describe the chemical potentials of A and B. In real life, engineering materials are not pure solutions all the time. In most cases, they are dilute solutions. So in real life, most solutions, including solid solutions, are dilute solutions. What exactly is a dilute solution? So let's just consider this. All right. This essentially is water and salt. The water is called a solvent, and salt is called the solute. What Raoult essentially said was that in a dilute solution, since the solvent is the dominant component, so in this case water, H2O, is the dominant component, most of the activity within the solution is the water molecule interacting with itself. He's introduced a new activity coefficient, gamma, to describe this phenomenon. What he's really trying to say is that the activity of A is almost the same as the mole fraction of A, because the amount of salt in a dilute saltwater solution is so infinitesimal that the interactions for water will dominate. Hence, the activity coefficient is pretty much 1, and all we really need to know is the amount of A that's within the solution. Where Raoult's law dealt with the solvent, Henry's law dealt with the solute. What Henry really stated is that the amount of activity in B is equal to the activity coefficient of B multiplied by the molar fraction of B. Essentially, all we have to do is to figure out what the activity coefficient of B is, multiply that by how much B is within a mixture, and we will be able to get the activity of B. However, what Henry did contend was that because there is such a small amount of salt or such a small amount of solute within a dilute solution, we can sort of imagine that the activity coefficient of B is essentially a constant. And so all we need to do is to figure out the molar fraction of B, and we will be able to substitute this into this. So in a dilute solution, the solvent essentially behaves like an ideal solution. Hence, the activity coefficient is approximately 1. Okay, so if we look at Raoult's law, which deals with the solvent in a dilute solution, the amount of activity of A is approximately the amount fraction of A. So it's really quite simple for us to figure out how much is the activity according to Raoult's law. When it comes to the solute, on the other hand, what Henry said that since salt is such a small component within the dilute solution, all we need to do is extrapolate this way, and we can treat gamma B, or the activity coefficient, as a constant in all our calculations. In short, these two statements sum up Henry and Raoult's law, which are applicable to dilute solutions. So essentially, the partial pressure of each component in ideal solution is equal to the product of its mole fraction and equilibrium vapor pressure in pure state, and that is really what Raoult's law means. Just remember that the amount of activity is equal to its mole fraction. And in terms of Henry's law, if the solute concentration XA of a solution A and B is low at constant temperature, then the partial pressure of the solute is proportional to its mole fraction. So what that really means is that the activity is equals to the activity coefficient multiplied by this molar fraction, where we assume that this is a constant. So now let's talk a little bit about real solutions. So this portion is a little bit abstract. Try and follow along. So first and foremost, here we've got three possible mixture examples. First, let's talk about the extreme case. So what this really depicts is the grain boundaries between two different solutions. And in this case, the AA bonds and BB bonds are very much stronger than the AB bonds. And hence, you are going to have to introduce heat to allow entropy to increase, be positive, to allow it to mix. What can also sometimes happen is this. A homogeneous mixture, whereby the AB bonds are stronger than AA and BB. And this, without much changes in enthalpy, would result in a homogeneous mixture and intersperse of material A and material B with each other. However, when it comes to solid solutions, we most likely will see something like this in real life. So this is a mixture of dilute solutions. In this case, AA and BB bonds are stronger than AB bonds. However, due to the ever-increasing entropy, we will tend to see certain AA bonds, BB bonds being broken to form new AB bonds to be interspersed within the dilute solutions. And so this is what we tend to see in most engineering materials. So this slide describes exactly what I was trying to say. So here, let's allow E to be the difference between AB and the average of AA and BB bond energies. For complete randomness, let's assume that E is equals to 0. And when E is less than 0, then there is a tendency for the number of AB bonds to increase resulting in an ordered substitutional arrangement. When E is greater than 0, clustering will occur since there is a tendency for AA and BB bonds to form. Now the effect of entropy increases with temperature. Now in real life, complete homogeneity doesn't usually occur. So this situation really is unlikely with very high entropy. It's also unlikely that we are going to see complete clustering, because the arrangement of atoms is usually compromised to give the lowest internal energy consistent with sufficient entropy to achieve the minimum free energy. Remember what this means? It means that it will reach a state of equilibrium. What is most likely is this scenario of a number of dilute solutions, and they will be amalgamated together in different phases. We could possibly call this the alpha phase and this the beta phase. Now the situation can be further complicated by the differing sizes of the atoms. If we had a mixture of two different solutions, whereby one of these solutions has an atomic size or atomic radius smaller than the other, the mixture is called an interstitial solid solution. If they were the same size and they were interspersed and homogeneously distributed within each other, it will be called a substitutional solid solution, which we've already described as unlikely. Most likely, we would be experiencing clusters within the solution itself, especially with atomic radii being the same. So let's look at a real-life example of a real solution, copper and gold. If you remember, at the beginning of this lecture, I mentioned that gold by itself, while a very valuable material, is likely to have very poor engineering material properties on its own. It usually has to be alloyed with something else, for instance, copper. So, in the case of copper and gold, they both have an FCC structure and are considered miscible in each other. At high temperatures, copper and gold tend to be able to occupy any lattice point at random. However, at low temperatures, they usually form an ordered structure of which you've got clusters of copper and clusters of gold, and they're usually arranged in alternate layers. So this is something known as long-range order. What this really is describing is the repetitiveness of copper, gold, and how ordered they are. So this is already extremely small in a copper-gold alloy. And past a critical temperature, usually the melting point, there is no long-range ordering at all, and copper and gold can be almost homogeneously interspersed with one another. A solid solution can be labeled as a disordered phase, which is here, disordered, when the atomic sites for atoms A and B are totally at random. A solid solution can be labeled as an ordered phase when the atomic sites for atoms A and B are extremely specific.